First of all, let me thank the organizers for this invitation to this nice conference. We had very nice talks. And okay, let's start. First of all, let me introduce the topic. I want to show in this talk that there are stronger grounds to believe that the Schrödinger-Poisson system is a double of a Newtonian embodied system. So let's first note that I had Newtonian in the title because in the previous title announced it was just embodied double. This is not true in general. This is just true for a Newtonian system, meaning that the Newtonian dynamics is given by n bodies that interact via Newton gravitational field. Okay, so first of all, motivations. Motivation in this framework is the study of large-scale structure formation in the universe. I will use all data and all simulation. This is a deliberate choice because all what I will tell about today concerns just order of magnitude and semi-qualitative considerations. So it doesn't make too much sense to be very precise in the use of densities, masses, and so on, lengths, and so on. As you will see, these conclusions depend very weakly on the exact value of the parameters that we will use. But nevertheless, let me say that this is inspired by the fact that the Schrödinger-Poisson equation are used to modelize the formation of structures at cosmological scales. So for measure of structures, this is also an old image, is essentially due to the gravitational action of matter. And of course, you need dark matter in order to form the structure you see, because if you use just ordinary matter, there is not enough mass to form the structures that you observe. Anyway, in this talk, I will talk about matter, meaning both baryonic and dark matter. The universe is homogeneous and isotropic at large scales, where dark matter can be successfully described as a dust fluid. However, this description breaks down at shorter scales, because the dynamics become nonlinear. Indeed, you have to use different methods. And one of the methods used to describe the formation of large-scale structures is based on Newtonian n-body simulations. Why this work? Because velocities are not relativistic, so Newtonian dynamics is appropriate. Therefore, you can use you can describe the system as a Newtonian n-body system in which the n-bodies are galaxies surrounded by dark matter halos and so on. And of course, you have to put this Newtonian n-body system in an expanding universe to account for the expansion of the universe. And this is done taking a background scale factor, which of course then fills the back reactions of fields. Okay, this is a review on this kind of computations, but and this is a whole simulation by Millennium 2005, which was already very successful in describing the formation of structures. Now this is updated. The last simulation have like 10 to the 4 more particles. So for order of magnitude higher in n. However, this is enough for what I want to show you. So this used 10 to the 10th identical bodies of mass 10 to the 9 solar mass. Therefore, these are galaxies. And these are made of stars, galaxies, dark matter halos, and so on. And this simulation successfully describes this formation of structures at large scales. Okay, and this is fair enough for what I'm talking about today. Just to tell you that n-body simulations as true n-body systems are very difficult because the number of bodies is huge. Therefore, in many practical purposes, the n-body system is replaced by a Vlasov equation. So this is just an equation for the phase space probability densities of the distribution of these n-bodies, and the coupling is gravitational. Here you find a reference. Okay. Well, it has been realized that it is possible to describe this n-body system by means of a Schrödinger-Poisson couple equations, in which you have a Schrödinger equation that is coupled to the Newtonian potential, and the Newtonian potential is sourced by this the modulus, the square modulus of this wave amplitude, and the interpretation of this wave amplitude is distribution of number of galaxies in the universe. So this is the mass distribution. So this is basically the density of bodies which sources the Newtonian potential. And they also take into account the expansion of the universe because they consider the scale factor here. Okay. So a few words. This is an effective model. And until now, the level of understanding is that it works because it works. There is no, at least if you read the references, there is no deep understanding of this. But I want to convince you that there is a way to explain this numerical evidence, let's say. It's important to say that h bar here, it's not the Planck constant. It's a parameter which has dimension of action, of course, which is like 70 orders of magnitude bigger than the true Planck constant. Okay, and of course, the parameter that drives simulation is the effective Compton wavelength, which is basically fixed by the ratio of the two important parameters here, which is the effective h, the ratio between h and m, which are three parameters. Okay, this parameter also controls the cross-graining of this simulation, because this effectively must satisfy this relation. Okay, but at this level of understanding, this is just an effective model. Okay, and I want to show you that there is a way to understand this. Just to tell you that, of course, also assume that this is the true Planck constant. But if you do so, in order to achieve an agreement between simulation and what you observe, you have to assume an extremely small mass. So this is what is usually called fuzzy dark matter, or axions, or scalar dark matter, whatever. There are plenty of models that use this very small mass. Okay. So there is this correspondence between Schrödinger and Poisson equations and the Newtonian n-body system. And I'm asking about the theoretical basis of this correspondence. What I want to show you that you can justify this correspondence using these two ingredients. The first one is Nelson stochastic quantization, and the second one is Calogero conjecture, which is based on Nelson stochastic quantization. So first of all, what is Nelson stochastic quantization? For what concerns this talk, you just need to know that if you consider a Newtonian particle that is moving under the action of a random force with zero mean, then it can be shown that the probability distribution of finding this particle at some position is given by the square modulus of a wave function which satisfies the Schrödinger equation. Okay, and here V is just potential of external forces. Okay, then we can use that, of course, if a particle undergoes a stochastic noisy force, it can be described in terms of a wave function. This is what is called Nelson quantization, but I don't want to enter into discussion of this. The second thing I will use is the ecological conjecture, which is based on Nelson quantization. This is based on this very generic observation that gravitational is universal. So every particle in the universe must feel gravitation. It is long range. So any particle in the universe must feel the gravitational action of all the other particles in the universe. The universe has a granular structure, very important in this framework. So we will assume the universe is made of particles, and especially we will assume that the universe is made of nucleons, which is, of course, not true, but it's a good approximation. And the other point is that the Newtonian n-body system is highly chaotic. So if you have a huge number of particles that interact gravitationally by Newton, classical non-relativistic force, the system is highly chaotic. And when these particles are distributed homogeneously in the universe, of course, they produce an extremely small and chaotic background force, which, by hypothesis, Calogero postulate is the origin of quantization. This is a very strong assumption. I will not use it. I will use it just an effective conclusion. I'm not stating that this is the true nature of quantization. And by means of qualitative arguments that I will show in the detail in a while, it's possible to estimate the effective order of magnitude of the Planck constant in that way, using, of course, a gravitational constant, the radius of the universe, which is just the Hubble radius, the mass of the universe contained, of course, in the Hubble radius, and the number of particles. Remarkably, if you use the radius, mass, and the number of particles in the observable universe, which is contained in the Hubble radius, you obtain an estimation of the quantum of the Planck constant, which is in order of magnitude correct. It coincides plus or minus one order of magnitude with the Planck constant, and this is very remarkable. This has been presented in this couple of papers by Francesco Calogero. I'm not stating that this is true nature of quantization. I will use this. And how you can obtain this result? You use basically dimensional arguments and semi-quantitative arguments based on the properties of n-body systems. Well, relevant quantities are the number of bodies, gravitational constant, and two between mass, density, and radius of the universe. Of course, if you fix two of these, the other is fixed. Okay. So with these dimensional quantities, you can construct a characteristic time, velocity, acceleration, energy, and action. Okay, time is fixed. Of course, all this is fixed by dimensions. So the time characteristic time must be this. Characteristic velocity must be just the ratio between r and this time. The acceleration is just the gravitational acceleration felt by a body which is outside of a sphere of radius r with density d. So this is very intuitive. The energy is just the gravitational energy, and the action is just the product of this energy and the time scale. So all this is fixed by dimensional considerations. What is not fixed is the rule played by n, because it's adimensional, of course. So you can introduce the n dependence in several ways. And we want to justify this assumption, where this tau is the characteristic time of the noisy background gravitational force. This is the time scale. And I want to convince you that this is the right dependence from the numbers of particles in the n-body system. Well, so we want to estimate this characteristic time. We know that this characteristic, the stochastic character of the noise is due to the granularity of the universe. And this is plausible that the characteristic frequency be larger, the large is n. So, since this is a collective effect, it's also plausible to assume that the dependence will be from the square root of n. So if you make this assumption, and you also estimate the energy, gravitational energy per particle, which is of course the total energy of the universe divided by the number of particles, you obtain this estimation of the action as characteristic energy per particles times characteristic time scale of the stochastic background. And that's the way you obtain the estimation of H obtained by Calogero. Okay. So again, the exponents of the dimensional quantities are fixed. This is not fixed, but I will justify this in a while. So if you assume that the universe is made by nucleons, and you make an estimation of the number of nucleons, which is very, it has very big error. And you also use an estimation of the Hubble radius, which is quite large error, and also density and matter. You have an estimation for the Planck constant, which is quite good if you compare with the true value of the Planck constant. If you think on how you obtain this estimation, this is like a kind of miracle, and the dependence on the exact value of these parameters is very weak. That's why I told you at the beginning I will use all the data. It doesn't make too much sense to use very precise data if you have such weak dependence of the precise value of the parameters. Okay. So again, I will use these. I will not state that this is the true origin of quantization. How can we justify this scaling law for the characteristic time? We have to go a little bit in the details of n-body systems. So you can estimate, you already have a value for the characteristic acceleration, gravitational acceleration of particles. So you have a value of characteristic acceleration, which is much less than for instance, the gravitational acceleration on the Earth. And this is the expectation of this stochastic time, the time scale of stochastic oscillations. This is the typical velocity you expect. So just acceleration time this time scale. And this is characteristic length. Note that this is much less than the Planck scale. So if you really believe that this is a true origin of quantization, you probably can find a lot of arguments against this interpretation. Anyway, I will not use this, but so how can we estimate the dependence of the time scale tau on the number of bodies? We consider the Hamiltonian of the system, and then we separate the motion between macroscopic motion and the microscopic motion given by this Lj function of time and Vj function of time, which are the position and velocity correlated to this microscopic stochastic noise, while this capital R and capital V are the macroscopic position and velocities. Okay, so on the short time scale tau, position and velocities, capital R and capital V, can be considered constant. So you can expand these around these values, and you obtain that at well, of course, typical velocities are of order nu, and typical length are of order L, so this justifies our assumption. So at zero order, you have just the zero order Hamiltonian, which is a constant in this short time scale. At next order, you have that these two quantities. The first one is W, which is the sum over mj Vj macroscopic velocity times nu j microscopic velocity. This must be equal to these two quantities, which here you have a sum, and here you have a double sum. Okay. So the sum in the first two terms contain randomly distributed signs, and this is why these two terms will be proportional to square root of n. Okay. While the underlying assumption, very important in the derivation of this result, is that the difference between macroscopic positions, L, is correlated to macroscopic position, the difference in macroscopic position. So if these are correlated, then these are all, these scalar products are all positive. And instead of having just an m here, you have an m squared, like this. Okay, this is a fundamental assumption. We have to keep this in mind because all this is based on this assumption. Okay, if you do so, you have this that this term, the G1, is negligible small in comparison with G2. So you have this this relation between W and G2, and if you extrapolate from this relation the characteristic time tau, you find exactly the dependence that we postulated at the beginning. So it scales as the inverse square root of n. So this is a justification of this strong assumption in the ecological conjecture. And this is based on this assumption of this correlation. Of course, what can be one possible interpretation of this correlation? Of course, if this is the comoving position of the two bodies, assuming that this difference is correlated to the difference between the macroscopic position, that could be explained in terms of a stochastic small noisy term in the scale factor of the universe.
Totally non-local.
Totally non-local. Yeah. Yeah. Well, the Schrödinger-Poisson equation are non-local. So, what are the limits of Nelson calorical quantization? First of all, at fundamental level, it's hard to believe that this is the true nature of quantization, but you might believe if you wish. However, there are several things that are not contained in this treatment. For instance, the collapse of the wave function, entanglement, and so on, because quantum mechanics is not only the Schrödinger equation. It also is related with the postulates on measurement, on the collapse of the wave function, and so on. But I will come back on this in a while. It does include fields, at least at this level of treatment, and it is non-relativistic. For instance, one might ask, what happens when you go back in time until radiation domination? How can you include photons in this treatment? Of course, you can't, at least at this level. So, but we are less ambitious. We just want to use this argument to show that in cosmological simulation of large-scale structure formation, it is justified by these two arguments based on calorical conjecture to use Schrödinger-Poisson equation as a double of n-body system. Okay. Well, so what's the picture? You have this n-body Newtonian system made of galaxies of whatever, and it is in simulation. This is placed in an expanding universe. Very important, because I told you that the fact that you consider correlation between microscopic and macroscopic displacements can be interpreted in terms of stochastic noise component in the scale factor. You assume that this embodied Newtonian system quantizes a la Nelson based on the Calogero conjecture. So you have all the the ingredient used in the Calogero conjecture. And what is new is that now you have a criteria to estimate the value of the effective Planck constant used in simulation, which until now was just a free parameter. You remember I told you that they use H bar to fix the Compton, effective Compton wave like in the simulation, or if you wish, the cross graining of the simulation. But you have the agreement between embodied simulation and this Schrödinger-Poisson equation just for a range of this effective Planck constant. So if these arguments are correct, now we have a criteria in order to give an estimation of this effective Planck length in terms of the parameters of the embodied simulation. And so we would like to verify this correspondence by numerical experience, okay? This is, of course, very difficult, but and I'm lazy, so what I did, I used simulation already done by other people. So I used Millennium simulation, but this is, I mean, it's just not because I'm lazy, but because this is enough.
You're lazy but smart.
Yeah, well, thank you. I accept this, but it is enough in the precision of our prediction. It doesn't make too much sense to be more precise because we are talking about order of magnitudes. So I used the Millennium simulation, and I estimated by means of this relation what's the expected value of the effective Planck length in this simulation. I obtained the if there was the speed of light here, this should just be the effective Planck length. So this is basically the effective Planck length is 10 to minus 4 megaparsec. And I compare with simulation made by means of Schrödinger-Poisson equation. So, well, the last sentence is it was that this is just remarkable, in my opinion, that this is the second time the miracle occurs. The first was with the Calogero quantization, the second with this correspondence between Schrödinger-Poisson equations and embodied Newtonian systems. So, however, you can ask whether this is a robust argument. So we need ad hoc numerical simulations to verify this correspondence, especially to check how this effective, if this scaling law of the effective Planck constant is accurate, when it becomes to be accurate, for how many bodies you have to consider at least, and also test the rule of the scale factor, which is very important in this correlation between the local noise and the macroscopic positions. Okay, this is very important. And for instance, you can check whether a simulation that does not make use of the scale factor gives the same result. Probably not, unless the system self-organizes in some way that this correlation emerges, but there is no evidence, no argument for that. At a more fundamental level, you can also ask whether this Calogero conjecture is in some, at least in some range, accurate. For instance, does it play some role in wave function collapse? We had very nice talks in the first day by Catalina, by Christian Pisticchia and Angelo Bassi. And they start, well, they have also experimental limits on the models for collapse, for wave function collapse. Of course, here is a little bit different because for collapse you need two ingredients: nonlinearity, which you have, and stochastic noise, which is not explicitly considered in this Schrödinger-Poisson system. However, when one might ask whether there is some way to calculate the expected noise in the Schrödinger-Poisson, and a working hypothesis might be that you first can consider, for instance, a noisy perturbation of the scale factor, which I think you don't have in your model. Might be, who knows? Then this must be generalized to fields, as I told you, and extended in the relativistic framework, which might be interesting for what Matteo Lulli presented last day, because if I'm not wrong, you quantize gravity assuming a noisy multiplicative term that you put by hand, and then you derive a relation of an emergent dark energy there, right? An emergent lambda.
That to me connected to non-linearity in the component, and this non-linearity can be
so but for instance, if you find an argument to justify this stochastic noise, you in principle find some relation between the dark energy density and, who knows, the effective Planck constant in this. That will be very remarkable.
Yeah.
So this is very interesting. So just to mention that there was a call for interest. Let's say that the president of Gruppo Nazionale di Fisica Matematica in INDAM was asking to members whether they have some proposals for joint project with Istituto Nazionale di Fisica Nucleare. That might be an interesting project if some of you is interested in this argument, in these topics, and we can make a proposal. That was before the summer, and the president of GNFM told me that this will be discussed after in the fall. Anyhow, I think that there are overlaps with people working in wave function collapse, and even with Antonino and Matteo. So we can discuss. Of course, this is a very naive argument. It's not mathematically, well, the physical grounds are motivated. The mathematics, of course, it's a little bit naive. So we are talking about the order of magnitude. Nevertheless, it might be improved, the mathematical treatment, and embedded in some solid mathematical framework. So that's it.